Hi, thanks for joining me. As you can probably tell from the title of this video, I'm going to be showing you how to prove not Fermat's last theorem. So it's a theorem which is similar to Fermat's last theorem, but not Fermat's last theorem. Now, in fact, my most popular video on the channel is titled How Not to Prove Fermat's Last Theorem, and that's sort of a false proof video of Fermat's last theorem. It's kind of jokey, and if you haven't checked it out, I recommend you go and check it out. I'll leave a link in the description below. But today I'm going to be proving a theorem which is not Fermat's last theorem, but very similar, and this is essentially this equation here: x to the n plus y to the n equals z to the n, where x, y, and z are integers, but in this case we're going to have n being equal to minus 1. So we have this equation here: x inverse plus y inverse equals z inverse, where x, y, and z are positive integers, and this is sometimes known as the optic equation. Anyway, we want to find all x, y, z in the natural numbers, satisfying this guy here. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so what's really cool about this equation is firstly, there are indeed solutions to it, which you might think isn't possible because of Fermat's last theorem, but that's not true, as we'll see in this video. Secondly, there are infinitely many solutions. And thirdly, in fact, we can write down each and every solution to this in some sort of parameterized form. And that's what I'm going to be doing today. So we have this equation here. One thing that we can point out is firstly, we can assume without loss of generality that x, y, and z are co-prime, because if each of x, y, and z say had some common factor, say 3, then we can divide each of x, y, and z by 3 and obtain a new solution to this equation. So we'll start off by assuming that x, y, and z are co-prime, and then at the end, to get all the solutions, we'll just multiply through by some arbitrary factor. So x, y, and z are co-prime, and what I'm going to do is just multiply through by x, y, z. So on this side I'll have yz plus xz is equal to xy. Then I can bring everything onto one side, so I'll have xy minus yz minus xz equals 0, but then I'm just going to add on z squared to both sides, so I get this equation here. And the reason I want to do this is now this left hand side is perfectly factorable, so I can write this as x minus z, y minus z, and that equals z squared. So just to see going from this line to this line, let's just expand this guy out. We get x times y, so xy, x minus z gives us the minus xz, minus z times y gives me the minus yz, and minus z times minus z gives me the z squared there. And then of course I've got this z squared on the right hand side. Now what we want to do is look at this from a number theory point of view, and we're going to suppose p is some prime number that divides z. So p is a prime number, it divides z, then of course that means that p squared will divide z squared, which means that p squared will divide this left hand side here. Now I claim that that means that p squared either divides x minus z or p squared divides y minus z. And the reason I say that, or the only other option, is that p divides x minus z and p divides y minus z. But if we had that, then we'd have p divides x minus z and p divides y minus z. But because we know p already divides z, then this equation here implies that p divides x, and this one here implies that p divides y. But then we've got a prime factor that divides z, x, and y, so that contradicts the fact that we're assuming x, y, and z are co-prime. Okay, so this doesn't happen. So we have then that p squared must divide either this guy or this guy, and this argument holds for each and every prime factor of z. So we apply this argument for each and every prime factor of z, and then from that we can deduce that this guy here is just a product of prime numbers squared, but in particular it's a square number, and the exact same thing holds for this guy here. So we have then that x minus z is equal to some square number, so m squared, and y minus z is equal to another square number, say n squared. And then of course from this we'll have that m squared times n squared equals z squared. So that just tells us that z is m times n. Okay, so then combining these, we get that x is equal to m squared plus z, which of course is mn, so m squared plus mn. Y is equal to n squared plus z, which is just n squared plus mn, and z is just equal to mn. So now what we've got to do is just check that this indeed does define a valid solution to the optic equation, and then we can multiply through by our arbitrary factor, and then we'll be done. Let me clean up the whiteboard and we'll continue. Okay, so we just showed that if we have a co-prime solution to this equation, then it must be of the form x takes m squared plus mn, y takes n squared plus mn, and z equals mn. So we just got to verify that this indeed does satisfy the equation. So let's just plug it in. So So on the left hand side we get 1 over x plus 1 over y, which is 1 over m squared plus mn plus 1 over n squared plus mn. And what we're going to do is subtract off 1 minus z, so we're going to show that this quantity then equals 0. So we're going to subtract off mn. And as you can probably guess, we're just going to multiply through by this sort of denominator. So we're going to multiply through by m squared plus mn times n squared plus mn times mn. So on this guy here, we're going to get mn times n squared plus mn plus m squared plus mn times mn plus m squared plus mn times n squared plus mn, oopsie daisy, all over this common denominator. And I'm just going to call the common denominator alpha for now, just so I can save space and save writing. And let's just expand this out, or have a look at what it expands out to. The mn times n squared gives us mn cubed. But then if we look for an mn cubed along here, we're going to get an mn cubed from this guy here. Oh, this is supposed to be a minus. So those will cancel. This mn times mn and this mn times that mn is going to give us a 2m squared n squared. But then here we've got an m squared times an n squared. So that's 1 m squared n squared. And then we get another one from this m squared times this n squared. So those will cancel. Okay, and then finally, this m squared times this mn gives us an m cubed times n, and then that's going to be from this m squared times that mn there. And that's why this all cancels out to 0 over alpha, which of course is just 0. Okay, so that shows that this guy here satisfies this thing here. So if x, y, z is a coprime solution, then we know it takes this form, and in fact this is indeed a valid solution. And then remember at the start I said we're going to multiply through by an arbitrary factor. So that in fact tells us that x is of the form, say k times this guy here, y is equal to k times this guy here, and z is equal to kmn. Okay, so k is just some arbitrary positive integer. So you have x equals k times m squared plus mn, y is equal to k times n squared plus mn, and z is equal to k times mn. And this indeed gives us a generic solution to the optic equation. And this is in fact every single solution to the optic equation takes this form here. And that solves our problem. So yeah, I hope you have enjoyed this video. It's quite similar to Fermat's last theorem, but a lot easier to show that, well, there are solutions for, and Fermat's last theorem obviously has no solutions. But yeah, this is something I can cover in, a 10-minute video. And anyway, I hope you enjoyed it. Thanks for watching. I'll catch you in the next one. Have a great day.